additive manufacturing. I'm working in this particular area for last, I think now 11 years or so, more than 11 years. So made lot of machines for wire arc additive manufacturing. My first very complicated part was in 2013 in IIT Bombay when I was working on a hybrid machine. That was my PhD, and built a design, not built, built. It was built by another company, and I designed a machine which was 5 meter long, and it can do multiple, stations were there. I'll explain about that. But my this is my core research area, and I am particularly somewhere between Dehradun and Haridwar. I am from Uttarakhand, and there's a village called Bhagwanpur. I'm from that place. I did my bachelor's from GB Pant Engineering College, Pori. It's in Uttarakhand again. It's a government college there. And then I did my master's from IIT Guwahati. And a part of this master's I did from TU Stuttgart. And then I joined IIT Bombay for my PhD. And I came back to IIT Guwahati after that, now recently. Before I begin, I think already many deadlines are over, but still, please note this conference which is going to happen in IIT Bombay. We invite you to this conference if possible. This is called International Conference on Additive Manufacturing and Characterization, ICAMC. Okay, so this conference is going to be in IIT Bombay, and it's being coordinated by Professor Sushil Mishra of IIT Bombay. And we this particular conference is going to be very unique because it's first of its kind in the country, and we are four partners in this conference. Bombay from West, from South IIT Madras, and then IIT Ropar from North, and from Eastern region we IIT Guwahati. So we are the zonal partners in this particular kind of a society which we are creating on additive manufacturing. So if you join here, you will see more than 60 lectures. I mean, you name the person, you will find that it's here in lecture. एक घंटा बाद. So uh, uh, you can search for about this conference on additive manufacturing. So all my I did like my BTech from Pori, masters from Guwahati, and PhD from Bombay. They are the most beautiful campuses in the country. One of the always in top 10, and you can see even from the images how beautiful they are. The common part in all three was the leopard used to visit all of these, all three. You can see the news here. They spotted a leopard in the campus, even inside the laboratory once. Leopard, and the leopard was visited. I mean, spotted in Pori village. Leopard visit. I mean, spotted in near IIT Guwahati. Even now, it's very recently we saw a leopard in near my house itself. So, but I do work in additive manufacturing. So, in additive manufacturing, so you, it's like the fifth day I know, and then I'm very sure that all of you are very familiar with additive manufacturing. So I'll not bore you with that, but I'll show you something interesting video, which I always share whenever I deliver a lecture on 3D printing or additive manufacturing. You see this bird here, but this is Mhm. Something is happening.
Professor, sorry, professor, sorry, professor.
Okay.
It is.
Okay. So this particular one, in which you will see the advantage and disadvantage of this technology just in a single video. These are the limestone caves. If you visited a cave, I'm not sure, but there are a few in Meghalaya as well. If you get a time, you should come and visit. These water drops, when they leave the roof of the cave, they leave two material behind, one on top of the roof and one on the bottom. These two material keep growing, and finally they meet, and a column like structures are created, like you see here. From nowhere, suddenly in between a column in the cave. This was not done by cutting the material. I mean, these structures what you see here were not created by flow of the water and water cutting and creating it. No, no. They were created by additive manufacturing, by depositing layer by layer. And the growth rate of these columns are like 0. I mean, few microns in a year. very slow. But maybe it's slow, but can you really fabricate it by any other method? By cutting, can you do that? No, it's very difficult. But of course, it takes time. There are advantages and disadvantages. So we have to choose this technology wisely. I say that again and many times before as well. We should not just look at this technology, fall in love, and just utilize it for something. No, that's not going to help. Uh, we have to choose it where it's required really, and we have to first understand all the process, and then we should choose appropriate one. So, of course, 3D printing, many names are there, right? Many keywords: 3D printing, layer manufacturing, additive manufacturing, solid freeform fabrication, digital manufacturing, rapid prod, all are same. Why each and every name is given has a particular reason. It's not like suddenly somebody came and said, okay, let's call it digital manufacturing. No, there is a reason why it is called digital manufacturing. There is a reason why it is called solid freeform fabrication, why it is called rapid prototyping, rapid tooling, rapid manufacturing. Huh? So I'll not go into this, but if you are interested to know that, you can have a look at my lecture in NPTEL. I mean, that's available on YouTube. I'll give you that knowledge in the end about that, how to find my lectures. Those are completely free. 42-hour content is available. That's covering entire additive manufacturing thing. And then the good part here is, and it's because of that it's fully automatic. Of course, the process is completely automatic, if starting from creating the file to building the part to the post processing. You know that you take a CAD file, convert to STL, do the slicing, of course, right? And if required, you provide generate support structure also if you are depositing on the edges and there are overhanging reasons to be realized. Now what is difference? I mean, this step remains same, this first one. And in the end also, okay, you have to remove the support and finish. What is varying, I mean, there are multiple ways of doing is how to add the layer. Either I should just join it by glue, or I should join it by melting, or what, the way. So that's the way, you know so interesting part is how to stack these layers together, and that is defined by ASTM by simple 7 method. Okay, ठीक है, you can join these parts, and layers can be joined by 7 way, in by 7 different ways. Either they are photopolymerized, or you inject the material just like your printer, 2D printer, right? That just like deposit, drops of the material on the paper. Similarly, you just keep doing it, and grow in Z direction, you keep doing that. Or you are injecting binder. You know about this technology in which we spread a layer of powder, and then the binder falls from the top. That either the binder or the ink which is coming from top has a binding agent, or the material itself has a binding agent. That's different story. It's like you spread a layer of, maybe cement, and then putting the drop of water wherever the water falls, it got hardened. Material extrusion, yes, you can do material extrusion as well. Sheet lamination, in which you are joining sheets together. So material extrusion, right, that FDM process. I mean, of course, the concrete printing also falls into this category. Sheet lamination you might have not seen, I believe, but I'll show you. We have one sheet lamination also now. We use metal sheet joining together by FSW, but of course, you can join even papers together and create structures. Powder bed fusion, that's the most popular one now for metal, right? Of course, it is for plastic also, earlier called SLS there, and then SLM particularly for making the metal parts. And direct energy deposition. In directed energy deposition, we feed the raw material in a melt pool created by laser, arc, plasma, or anything. Correct? And then you build parts. So these are the 7 different methods. Whoever might have delivered a talk would have definitely choose a particular process to explain. Like for example, I believe Pratik uh, must be delivered on lecture on, as you mentioned, metal printing using, I think, extrusion process, which required post processes. So in that case, I'm very sure Professor Pratik has discussed about this technology called material extrusion. His technology falls into this. And then like CP Pauls or might have talked about the laser based DED based system. I mean his process falls in under this category. and and so on. I think you can now map easily. So there are more than, under each of these category there are more than 10-50 types nowadays. So total, if we can name more than 50 different type of additive manufacturing processes, but nicely they covered ASTM. But you can also classify in a different manner, like what is the raw material being used, either it is liquid, solid, or gas. If it is liquid, how to join liquid, either you photopolymerize it or freeze it. If it is wax or water. If it is solid, it could be sheet, powder, or wire. Correct? Or gas, I didn't see anything in which one gas, two gas came together and make solid. No, that may be in future, and you can think about it. uh, and then of course I tagged it like T1, T2, T3, and then you can see I'm categorizing the ASTM here. You see that multiple categories are further falling into the groups. So the point here is, whatever you are developing, you should map it always with that. That helps you for writing papers, because nowadays many journals clearly say that bring the conventional, I mean the standard way of name for your additive manufacturing process which you are telling. FDM, many good journals do not really accept that term, because it's for a particular machine, while the technology should be called as the material extrusion, or for more particular, fuse filament fabrication. Correct. So these are the, you know different type of 3D printing processes. This is wet photopolymerization. This is, sintering. SLS, the powder bed fusion. Material extrusion, direct energy deposition using powder. This is the wire arc additive manufacturing using welding guns. Correct. So I'll talk about this particular one a bit. Though let me tell you, it's not at all new. I mean, somebody says that he invented this. Not really. I mean, it's the oldest, 3D printing process. See the patent. It was filed in 1920, where there was a patent in which it is written that we are claiming a method of making decorative articles. So they say that take a welding gun and keep depositing in your hand the material, and you will make decorative articles. Of course, they said decorative because they might have believed that that time not enough strength will be there, but and the hand movement may not give you, perfect shapes. So it's okay, but the hand has been replaced by the robotic arm now, and the weldings are a bit more sophisticated. That's all. And of course, you have a software which can, move this robotic arms in a particular path. That's it. Otherwise, this is not really a new technology. But I'm going to talk. But before somebody question, I know some of you maybe metallurgist. I always believe that this is an important question. Whom do you think a material expert, I mean a 3D printing expert, how do we know? I mean, how can we say that, okay, this guy is a 3D printing uh, researcher, or this guy research area is additive manufacturing? So because you might have met many people, and then their background, if you see, either they are like, you know PhD in finite element method, then they do simulation for DED maybe, or other process, or their PhD in material characterization. Their core area is characterization, and then they do characterization for additive manufacturing also. Correct. So they there are very few you will find who can talk about all seven processes independently, about the machine, how it works, about the software goes into it, irrespective of an expert in materials or an expert in maybe something. So those may have a doubt, of course, that fine, what you are telling may not work, correct? I mean, strength may not be good, roughness may not be good, many issues, of course you can tell. But let me tell you here, this is a video by Veritasium, a very good YouTube channel, you can check that. 3D printed rockets are already in space, huh? Already in space. That means it is possible, right? There is no doubt about that. Correct? The material gives you enough strength. It is just now you who will tweak the parameter, tweak the environment in a way that it can print for you or your application. Okay? It so RA value, even these printers are not even machined. They have surface roughness bad here, I know, but they said it does not really affect the aerodynamics of it. So how many types again? So we have a very unique method of classifying additive manufacturing systems. We do like this. I mean, you might have seen in some movies nowadays, right? When in a police station or something, they put a chart and they put a connection between different incidents or events, right? That's how we do investigate on different types. Like material, if it is metal, material is flowing continuously, not drop by drop. If machine kinematics is serial, parallel, or hybrid, and I'll show you what does it mean. Energy source is induction, arc, or energy beam. So we are focusing today on arc. Dr. CP Paul might have talked about energy beam, and in that energy beam also he might have talked about laser. But today I am going to talk about arc, and in arc also I'll talk about mainly MIG and plasma in the end. I may not talk about TIG today, but these are the possibilities. Whether you generate support or without support, if you don't require have mechanism for supporting the overhanging features, you have to use multi-axis like CNC machines, 5 axis CNC machine or robotic arms, so that you can tilt and build. So any doubt, uh, you may, like I said, intervene in between and ask doubt. That's what I like.
Yes, Professor. We have one question in the chat box actually. It is about measuring the residual stress, which is the reliable and most accurate procedure in measuring the residual stress in AM process.
Yes, I completely agree. This question very relevant and good question actually. Um, yeah, we have a portable XRD. You can put samples without cutting, because uh, most accurate method is of course the deep drill method. So I'll not go into that. I'll not talk about that. But why do you want to measure? You want to measure it for some mitigation. You don't want residual stresses in the part in the end. So better you can use directly the portable XRD. And why I like this method, I'll tell you. If you prepare sample for another way, like you want to do XRD, not portable, the in which you have to cut the sample, prepare it, cut it, polish it, and then measure the stress, it got relieved. The time you
The
cut
stress.
it, it's no longer constrained, right? If it is
Yes.
constrained, then only the stresses will be inside na. So I believe that you should have a system or method in which you need not to remove or cut the part. The machine can go there, measure it, and come back. So that's the portable XRD seems to be a future. Yes.
Okay.
Okay. So
One more
yeah,
question. How do
I
the XRD measure the? Okay, this is actually some theory
how
part of the
do the
question. First,
XRD measure the resolution?
yes,
Please.
yes, yes. This
ठीक है. There's a uh, what is that? Berg's law, I think.
Bragg's law. Yes, Professor.
Bragg's law, yes. So
Yes,
when a ray falls, there is a detector. If the plane is shifted, it goes somewhere else, and then the difference in angle you measure, and that's how you came to know that what is the stress level there. So that's how the XRD measures it. Huh?
yes,
There are different ways. Huh? So XRD
yes,
works on that. But there are other ways of measuring residual stress. If you do deep drill, maybe for example, in which you make a drill due to a deformation, its shape got changed, the whole shape, and then you measure the how much it got changed, because circle becomes ellipse. As you see that, let me show you. If equal stresses are everywhere, it will remain circle. If there are somewhere I get a stress, it becomes ellipse, na? So something like this they measure. There are many ways. I mean, a strain gauge you can use. Huh? You can make even grids in the back. It got deformed. Those are macro level, or you can go to diffraction level, neutron diffraction and all. I think, है ना?
Yes,
Uh,
Professor, I
uh,
have one question
yeah.
uh, about wire arc additive manufacturing for copper material. Is it possible? What are the
Tough, tough, tough.
difficulties?
टफ
Yes,
है
Professor.
क्योंकि इट्स a highly conductive material ना. The
Yes,
issue
Professor.
comes with the conductive material is it does not allow you to make the melt pool with the, particularly in MIG welding or whatever you are
Okay.
using. So
Okay,
that's
Professor.
very difficult. But
Can
another
anyone
issue,
tried, Professor?
yeah, I have seen stainless steel, and even they make copper and stainless steel FGM also.
Okay, Professor.
You can search. I saw, but
Oh,
I am interested in using copper wires but with plasma, because in
okay,
plasma,
Professor.
plasma is generated separately na.
Okay, Professor.
But then again, because of the substrate, which is again the copper, it will
Okay.
disseminate the heat so fast that it's very difficult to maintain the melt pool. So maybe some preheating, or maybe putting the whole thing in a hot environment should work. But it's a good research area, you can explore it. Yes.
Okay. Thank you.
Okay. uh yeah, Bragg's law, somebody wrote that. Thanks. Why? Oh, what is it? Dichlorine most preferred
Uh,
for debinding process in
Debinding
metal.
process, metal extrusion.
Ah, okay. This chemical, I don't know. I have no clue. Maybe Pratik is the right guy to answer this. Uh, Debinding process in metal extrusion. ठीक है. So I don't know why this particular chemical you are asking is being used. Uh, but I have no clue. So only Pratik, or maybe the one who works in that area. I have no idea. Okay, they use some chemical to remove it. I thought they some because I know how they do debinding for some ceramics printer. If you extrude or use wet photopolymerization to make the ceramic parts, those are called the green parts, of course. Then the green part put into the furnace, and they debind in the furnace itself. Due to heat, the other material got evaporated basically, or I mean, and then they use a very controlled heating, maybe hardly 1 degree per minute or so, very slow debinding, so slowly, otherwise the crack is the issue. And then they do final sintering after debinding, of course. But I'm not sure whether they use chemical as well. So that I don't know. I'm sorry. So good. I like it like this. So please keep asking questions. Yeah. Okay. Yeah,
In-
Rupam.
yes, sir.
Huh. So maybe, but keep asking question. I got bored really otherwise, है ना? So ठीक है. Now,
Yeah, before we get
I'll
into
come
the
back
lecture, Professor.
after 15.
Oh,
No, after 15 minutes I'll come back. So
okay,
keep
Professor.
posting. Keep posting your
Okay,
questions.
Professor.
Okay. So bhai, now this MIG welding, huh? You know MIG welding. I believe that many of you are mechanical engineers here, or of course the engineers. You might have definitely done MIG welding in your curriculum in BTech. So this is the wire. The wire comes. The wire itself generate arc. You keep feeding the wire. It got keep getting consumed, and you put a CNC machine either on the bottom on the substrate, or you move the MIG welding back and forth or in whatever direction you want. The wire keep on getting melted and keep on getting deposited. Correct? That's how it works. Simple. Very simple process. You use gas, either organ or organ CO2 sometimes, a mixture that's required for cooling. There are many reason for that, but you need not to worry. Definitely not to worry, because welding is an old technology. Everybody, you know, does welding. So whatever gas they use, you also choose that. Maybe some tweak you need to do, some in percentage optimization, flow rate optimization. Of course, that you will do. but composition is well established. Okay, it's not like not at all new. So welding का parameter you can use just to start with. Uh, but ठीक है, what should be the bead shape and size? Uh, you know that I believe, but let me revise your fundamentals if of the welding. If you have a straight polarity in which the workpiece is positive, if workpiece is positive, more electron will bombard towards the workpiece. Hence, more heat will get generated on the workpiece. Hence, you get a more dilution, like you see that, and the upper portion will be less. I mean, the bead height will be not much. Correct in that case. So, I don't want that much in the additive manufacturing. No, because if it is beyond my previous layer thickness, it will distort it, and it will just collapse the part. Lot of heat is not required. More heat, more issues. We want optimal heat. Or you can do in that case negative. If I do negative, workpiece negative, that means more heat will be bombarded onto the wire, hand deposition rate will increase, but it will not get much chance to get penetrated. We know that. In that case, ठीक है, less dilution, but then sometimes fusion issues also come, strength become very low in the z direction. Correct. And sometimes they say use AC, 50% up, 50% down. Fine, both are fine. Now let me ask you a question. I'll see you and explain this. Look at me. If I have two fingers, correct, I mean two hands, and in one case I am holding it like this. I mean, quite a distance I overlap, fairly a good amount I overlap. Strength will be good, right? If I pull now my hand up and down, it will require a lot of force, right? But if only my tip of fingers are in contact, then less force is required, right? Correct. So now you know why, if I print the part with a very low heat input or very low dilution, then grip is low. Correct. No much dilution into part, no much green got growth. I mean, a very small portion got fused. If I overlap a lot, of course it's good, but then there are issues with the pre-built layer got damaged. Correct. So, and that's why you know now that the strength is also bad. Yes, you can ask um, Kailasan, right? If can you pronounce your name also? Somebody raise the hand. Can somebody unmute him?
Kailasanathan sir, you can ask question.
Yeah, but he has to unmute.
Yes, I will actually. Yeah, he can unmute browser actually.
Oh, he can. Then
Yeah,
maybe by mistake he is
mistake.
raising a hand.
Yes.
Maybe. Or you can, type here if you are unable to. So fine. So that's why, in additive manufacturing, it is preferred to have AC. Chalega 50-50. But then, ठीक है, how do I transfer material? Is it like, do I do what I do in welding will work here? ठीक है, there are multiple ways. First is called short circuiting. Short circuiting, you know that, in which you touch the substrate. The short circuit happened. The wire solid form touched the substrate and the short circuit happened. And then machine came to know that, acha, there is a short circuit, increase the current. It increased the current. And as the current increases, I square R, you know that, more heat get generated and it got break. The wire got break. And detached. Again, the wire come further, again does the short circuiting. This is called short circuit. Why short circuit is happening? Because there is no enough current that the wire got melt before touching the substrate. It touched the substrate in the solid form itself. Correct, right? And or you can do globular transfer, in which there is a enough current that it makes the big bubble of the molten metal, and then it falls, the big drop. Or it can be spray transfer. In the case of spray transfer, it the metal falls onto the substrate like a spray. or pulse spray or rotating spray. Let me show you. Yeah, somebody is asking something. Okay, maybe by mistake. So you see this. All of them are summarized here. I thanks to this channel. This is a very good channel. I mean, they just nailed it. I mean, shown all. I just put them together, and you can see this is the short circuit. You see that the wire is touching the substrate, and you see the lights off. The lights off means arc off, है ना? And arc off means short circuit. And then the machine came to know it immediately increased the current, so that it got lot of heat here, and then break the wire, short circuiting, Gubler transfer. You see that wire feed is very low in this case. Wire is getting melted and getting accumulated here, and a big drop then falls. Or spray, the current is too high, that wire is getting melted here itself and coming or a pulsed one. This is interesting. I mean, I want definitely not these. They are a lot of heat generating. I mean, in this case, the spray transfer, a lot of heat has to be given. In globular transfer, big drop is falling. It will do spatter, right? When it will fall here, the molten metal will fall here and there also. Na spatter, you know that. So what I want is something in between. So pulse really works. You give high current only to detach one drop. Okay? If current is further increased, you see what will happen due to the multiple forces, those Lorentz force and all. The and because there's a magnetic field get generated here, and then you see that it keeps on rotating also. That's very bad for additive. We don't want that at all in additive. So preferably, what we don't want this, we don't want this, we don't want this much, and this also not really. Hmm? We want this, chalega, ye bhi chalega. These two are fine. Okay. But then
Can we say
CM,
these two? 1 minute, Sir.
yeah, yeah, yeah.
Yeah, can we say these two as the drop on demand method?
No, 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 not at all. Drop and demand is completely different. You want to learn about drop and demand? I'll explain today. Drop on demand uh, uh, is more like a CMT. I'll explain CMT now. Okay,
Okay, bros.
I'll explain. Good question. So fine. Then CMT came into picture by Fronius, and they said, "Okay, bhai, you want less heat, na? We'll provide more less. Where the extra heat is going in short circuit?" They said, "Okay, we will even reduce the heat then the short circuit." Okay, so you see, when the wire touches the melt pool, in this case, in the short circuit case, they increase the current, correct, to break it. So they said, why to increase the current to break? Instead, I'll pull the wire mechanically. So they see here, the wire is going forward, it's touching the substrate, short circuit happened. As soon as short circuit happened, the surface tension between this the melt pool created onto the substrate, and the drop generated at the tip is high, and they got better adhesion and got stick here. And you pull the wire back. Of course, if you pull the wire back very fast, what will happen? That it will leave the drop behind. And to do this, earlier what we were doing, we were increasing the current, correct? We were doing what? We were increasing the current. Then only it was breaking here. We generate more heat here. So we eliminated that extra current to break. That why to use extra current to break? Instead, I'll pull it by hand. They don't do it by hand, of course. They keep vibrating the your wire, and it is in synchronization with the current supplied with the power source. Very sophisticated system, and hence got very, very popularity. They call it as cold metal transfer. Cold metal transfer is not a generic name. Again, let me tell you, this method was later developed by Austria. Of course, first developed by Austrian company, Afronius, and then now by Japan also. There are few companies they supply. But they got so popular now that everybody, even in papers, you can read this term. But it's a commercial term patented by this Fronius guys. CMT, cold metal transfer. Even I am writing it here, correct? But the technique is now, I mean, I think being adopted by many because patent is no longer valid, I believe. And then Japanese and I think so. Now many other companies adopted similar technology. Hmm? This become very popular for additive. Okay, this is best. That's what we want. We want the substrate to remain cool and keep depositing material. Hence, today everybody uses CMT. This is how it works. You can see this slow motion video. Touches, pulls back. You see that? Somebody, it looks like somebody pulled it, na? So that tiny amount generated at the tip just got pulled back. But here the drops are in micro level. There are tiny drops getting generated at the tip, and you are dropping them. Of course, it can be called drop on demand also, like just now somebody asked. Correct. But this is not drop on demand. I'll let you know what drop on demand in additive manufacturing means. So fine. So this is the complete flow chart of MIG based warm. Of course, start with you know um, CAD model, prepare STL, all that you do. Then after that, you go to the bead library. You choose that which what should be my what should be my bead height and bead width, so that I can optimally define my layer thicknesses and all. Correct. And then deposition unit, and then of course we provide a platform on which we can move it back and forth and in whatever direction. Finally, the part got built may require finishing or heat treatment to release the stresses or get the desirable microstructure. And then of course, so if you are new to this technology, this is the step you should follow. First, you should do single bead experiments, see what is the width, what is the height. Then do multi bead experiments, deposit next bead adjacent, then multi layer experiments, and then you build the component and do the characterization in between as well. This is a typical trend of hardness in parts created by worm, and you know that the region, the hardness is high on top because less number of thermal cycle has happened here, but bottom lot of thermal cycle, na, heating, cooling, heating, cooling, heating, cooling here has happened many times. So the grain become coarser. They got merged with the neighbor grains also. Strength wise, of course, traditionally, if you see, the strength in this direction is low. In the Z direction, this is the Z direction strength, while the strength in other two direction, I mean in this direction or in this direction, are fairly good. They are good, but in this direction, like the build direction, not really. But as like I said, increase the current, the strength also increase. And you know the reason, I already explained the hand wala region. That okay, you grab it more. Just that's how you can imagine it, huh? But now let me tell you some defects. And the first important defect is residual stress. Residual stress. What is residual stress and how it got generated? First, let me explain that. When you heat, for example, you are creating a melt pool. It is getting heated. Hence, it's converting to liquid. As it get converted to liquid, it compresses the nearby area because volume is increasing. Correct. It compresses the nearby, pushes the nearby area. Hence the stress are compressive in nature. Then after that you cool it. When it get cooled, it this interface, because this is from here, it is going to get solidified, right? It will pull this region. As it will pull, in the end there will be stress remain there. That is called the residual stress, which remain in the part. Now what could be the issue? I mean, ठीक है, there is stress, so what? But if that stress is tensile in nature, you can imagine if this bottle breaks at, let us say, 100 force, so I have to apply 100 amount of force to break it. But if there is, let's say, residual stress inside this of 60 amount, that means only 40 is required to break it, na? 60 तो already था. Correct. And that's why forged parts are better, because in forged parts you hammer it. It has lot of compressive residual stress. Hence, if I try to pull it, or if there is a crack, it will not try to open it. The nearby material will try to even close it. So it's dangerous. That it should not be in the parts, the particularly the tensile nature. Compressive to chalega, we like compressive residual stress. But if the residual stress is more than in the part when you remove it from the job, if it is more than yield strength, what will happen? Or let's talk about less than yield strength. If it is less than yield strength of the material, nothing will happen. You can't see it by naked eye. ठीक है, looks good. But like I said, when you break it, fatigue करेगा, or maybe crack growth will be very fast. So you can't see that residual stress. For that you need to use your XRD and all that methods, है ना? But you can, when you break it, it will break like very easily. So if the stress is more than yield strength, it goes into plastic zone, meaning when you untight it from your fixture or whatever, taking it in hand, it got warped, meaning the stress got converted to deformation, correct? And if that stress is more than the ultimate tensile strength, you will see even crack, it will break. Hmm. So residual stresses are not good for us. The second is porosity. Porosity can be of different types. It could be raw material induced porosity. Maybe आपका raw material is greasy, not good, not nice, there are multiple uh, hydrocarbons in it, there are issues, contamination in the raw material itself. Or process induced. It can be due to poor path planning. For example, your drop looks like this. Then, of course, if I'll deposit another drop adjacent to it, what you will see? A hole, na? This tiny area. Lack of fusion. Correct? So, that also leads to sometimes these porosities. You see that my impeller, I built it in 2014 or 13 by additive manufacturing. This was by 3D printed. And after depositing, I saw these marks, and it was happening because I was in a hurry. My task was not to do the materials of it. I was working on tool path planning, CAD cam of it. So my what I was doing, I was depositing a layer and immediately switch on the coolant of the machine. Yeah, let it cool. It just happened fast. And then I deposit next without even cleaning the surface very appropriately. I clean it by a cloth, but not really bother much. And due to that, hydrocarbon got trapped, and then when I finished it, I see these porosities. Naked eye, otherwise it was not. But when I finished it, I saw that. But I could have eliminated. I have to clean the surface properly, or should not use the coolant, of course, uh, for cooling it. Yeah, and out.
Yeah,
Any
somebody mistakenly
inputs
opened
from
the
it?
mic.
Ah,
Yeah,
interesting. Anyway,
agree,
we'll take
Professor.
some questions. There are 5 questions now.
Yes, Professor.
Uh so I left nice information going on. Acha, that is
6.03.
fine.
Timing from 6.03, Professor.
Ah, 6.22 है ना? Is it
Yeah.
possible to get controlled microstructure and grain size in powder bed fusion? Techniques are also what type of microstructure we can accept in metal powder bed fusion in comparison to conventional casting. देखो, the first, of course, it all depends on the cooling rate, right? The microstructure, what you are realizing, and what kind of, I mean, you can even yes, control, you can even, people claim that they can make what you call single crystal in powder bed fusion. But then again, and how they do, they keep the bad heat, and then while depositing next there, they slowly increase or decrease the temperature in a way that they keep on manipulating the grain growth or grain formation by controlling the cooling rate. So yes, you can do that. There are multiple ways. I can give you one example. You can try that. For example, I'm depositing a layer. I deposit a layer. Imagine, it was a very long track. I mean, I was keep on depositing. I suddenly said that, nahi, nahi, in this portion I need martensite. I'll bring a, you know, uh, cryogenic maybe something, and I put that nozzle at that location. Quickly cool down, na? That portion only. Remaining portion did not, but that portion. Now you can see, rest of the portion has, for example, mild steel. You are depositing has the perlite and ferrite, whatever, uh, perlite and ferrite structure, ferritic structure, and but that particular zone will be martensite. Correct. You can do that. You can really control, but you need to have some auxiliary arrangements to control the cooling rates, either heating or cooling arrangements properly. A powder bed fusion ka you are asking, so I know there only flexibility is you can increase the temperature of the substrate. They do that, huh? But I hope you know that we are not discussing powder bed fusion. So how to minimize the cracks and voids on the manufacturer part. Like I said, the cracks and you try to eliminate the residual stresses, tensile nature of the residual stress. Try to minimize it as much as possible, है ना? And voids, like I said, you have to do proper path planning. Contamination should not be there. Uh, Gas induced porosity, if it is, you have to use appropriate gas. Gas is majority of time the issue. Huh? A reason behind that. Can we use nano composites? Use, or I think you want to say, can we make nano composites? What is nano composite? We made composite. Oh, I don't know what you want to ask, but I can give you an example. We made continuous fiber reinforced mild steel composites already. We have made tungsten rods embedded in the structures made of mild steel, and those rods are continuous rods. I mean, continuous fiber. So yes, we made composite, tungsten steel we made, titanium, aluminum we made, and now we are working on some other, I think, stainless steel and aluminum.
I want to add one point to that question, Professor.
Mm-hmm.
Can we spray some kind of nanoparticles while we doing?
Yeah, you can.
Yeah,
Yes, yes.
yes, Professor.
We tried. We tried. The issue is, I'll tell you the issue. I tried once, alumina, but
Okay.
MIG welding, TIG welding, they required your material to remain conductive, है ना? Because
Okay.
then only circuit will be closed. But if you mix alumina or something, then the conductivity lost. Hence, when you go up further layers, the arc establishment become an issue. Okay. So yes, but in laser you can easily. Though in this also people does some amount, does not really affect much. You can feed alumina or something. What about endurance strength of such component? Yeah, I mean, it's good. Again, such questions, I really love such questions. But just before you ask such question, remember the first slide. Parts made by this are already in space, so endurance strength is good. है ना? Parts made by this process are already in space. It is just now if there are bad endurance strength, we'll increase it. We'll do some post processing if required. But I see no issues till now in at least mild steel or aluminum. They are well established, even stainless steel. Some hard to weld material, of course, S13 and all, they create issues, but otherwise no. Hmm? What is the properties to check before going to select a metal wire for GMW? Good question. Yeah, chat. First of all, you should be find a wire which has the uniform diameter everywhere. I know how do you measure it, so buy it from a good manufacturer, and that comes over a period of time. Composition. So before you go ahead with deposition, cut it, do EDS. Don't believe the new vendor immediately. Better to cut it, check your own EDS, see that acha ha theek hai, there are enough exact element you want, है ना? Then you go ahead. So these things you should do. Otherwise it's good. Then it all goes on trust, huh? That once you
Sir,
finalize.
hello, excuse me.
Yeah, yes, yes, बोलिए बोलिए बोलिए.
Yes,
Stop.
Rishabh, you can ask.
Stop. Yes. Okay, I think I'll read the next. By polishing, is it possible to get mirror like? Yes, sir. Yes, yes. Even warm products. You can read papers published. My student, his name is Atul Singh Rajput. He is my student who has worked on, uh, what is it? Just let me. I want to message everybody.
You have to select everybody. Yes, Professor.
How do I select everybody?
Yeah, meeting group chat. That's all. First one.
Ah, yes, yes, yes. Atul Singh Rajput. Search his papers in my Scholar account, particularly his paper. He has done mirror finish, 1 nanometer level, to powder bed fusion, warm, everything. You can check that. Ah, cool. Rishabh left. Okay, he may come back. Something, maybe some connection issues. Is there a chance that the DED based manufacturing technique like VAM would compete with powder bed fusion to make each other obsolete? uh, yeah, of course. They have different strengths, sir. क्या है powder bed fusion is a magic machine. ठीक है magic machine means uh, press the button, sit back, relax, it will print. You do not require much expertise in the human who is operating it. VAM is not going to be like this. It is mounted on a robotic arm, 6 axis robotic arm. Now I'll show you 18 axis robotic system I have. 18 axis. No layman can operate it. It's like JCB. You can drive your car. Even people like me who can't drive, maybe I can manage with automatic one. But this is like driving a JCB. You can buy a JCB, but you won't find a driver. So VAM and but possibilities are endless. Powder bed fusion it cannot do at all. For example, there's a project going on in which this robot which is mounted on a truck and it will go to bridge which got damaged. It will just deposit there and come back. Powder bed fusion can't go there, right? So there are they have different. They both are going to work in a synergy basically, and I believe uh, VAM has a scope. It has its own audience, own capacities. Huh? Uh, what are the current research trend in plasma-based worm, particularly in India? So I have a project on plasma by Indo-German Science and Technology Center with Germany, uh, and I'll show you that. So that I don't think more than any that there is a facility that's very cutting edge facility. I'll show you that. Why additive manufactured parts are mostly utilized in forming based tooling, mostly and not metal cutting tools, sir. Very nice question, sir. देखिए uh, maybe you can answer it, Satish Kumar, right? Huh. So I have a die, correct? That die is forming die. That is making this bottle cup maybe. Just punching. Keep doing. How many of that die you required for 20 lakh piece, for example? One, correct? It is customized. So 3D printing is good in that. Less in number, customized. एकदम से you choose it blindly. हाँ 3D printing. I'll do 3D printing. Customized part, less in number, 3D printing. It is good because it 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 doesn't matter for 3D printing whether it is one part or 20 part. Cost remains same. You know that, right? So, but in CNC machine, for example, those tools making is not justified. People are making. I'm not denying. People are making already. Ah, but it is not justified. The method of powder metallurgy route is much more, economical to make those parts because they require lot. One cutter cannot be used for 20,000 piece, I'm sure. है ना? It has life. So 3D printing is not then justified. They said, okay, ठीक है, we need a cheaper technology for that. But if you can make a tool by additive manufacturing, cutting tool with multi-material, infinite cooling channels inside, integrated shapes, which cannot be by powder metallurgy, then yes, there also it has future. है ना? So you got it, I believe. One new message I got. What are the post processing technique required after removing support structures? Huh? No. So first of all, sir, there is no support people use in WAM. It's very difficult to remove. So support is not there. But ठीक है, as you ask, maybe you are asking for powder bed fusion. So yes, in powder bed fusion, when you remove support mechanism, yes, it leaves some marks there, and you need to either grind it or mill it. So by grinding they manage if it is by hand possible, or you can do, if you want chemical, I mean mirror finish like 1 nanometer. First you do grinding, then you do chemical etching. You put it in a chemical. One of the paper again of Atul Singh Rajput, you can read, in which he made the part on powder bed fusion, put it into an acid, surface got etched, reached to a desired level of surface roughness, then did the magnetorheological fluid based machining. It's a polishing process, and then reached to one micron of 1 nanometer level. So fine, I hope you got it.
Good evening, sir. One question from my side. Sir,
Yes, please.
is that for example in VAM technique we are building the material in layer by layer by melting the wire. So when I'm in like let me say 300th layer, I am currently now printing. So what about the thermal gradient variation of the first layer and the last layer, sir? Will it have significant impact on the failure or a fracture of the component? I mean,
Yes.
will it get differential fracture or differential strength, like varying strength comparing to the bottom and the top? Is there any difference, or it will be same throughout the structure, sir?
It is more or less same. Let me tell you, few buffer layers you can deposit, है ना? After 5 or 6 layers, there are good paper you can read nowadays. Recently published in additive, I reviewed it. It came to steady state. You know, after few layers, maybe for first few layers, it is quickly heat disseminating. Large substrate is there, which is acting as a heat sink, quickly disseminating the heat. But as you reach above a particular height, then it is not really. It just keep disseminating the heat in that same fashion. Quite a steady state is achieved, and hence thermal gradient of course remain exactly same. So you see the time lapse of these parts, you will see that trail continuously going up in a very similar manner. Correct. So that's steady state is achieved. So I didn't see much difference, and if it is maybe some material, those are very sensitive for that, but steels, nothing, nothing
Is
much.
it possible to do copper in wire
It's
additive
tough,
manufacturing, sir?
tough like I already said. Lakshmi asked about that. So
Because of
yes,
reflectiveness or
there is no reflectiveness issue in arc, right? We are not using laser, na. Laser has a reflective. Reflective is for what? Light, na. Light
yes,
got
sir.
reflected, and laser is
Will it
light. Arc is not light, hai na. Their issue is conductivity. It's so conductive that it does not allow bigger melt pool to get generated. Tough to maintain that melt pool due to conductivity.
we need some controlled room temperature for doing this
Yeah.
fabrication of copper, or what?
Substrate heating, some people do, or increase the current too high. But if you increase the current too high, spatter happen. So there are issues with copper, mainly
Thank you, sir.
from the conductivity side, not the reflectivity side in arc. Reflectivity it doesn't matter for arc.
Will it suitable for large dimension parts, sir? Copper.
Very. Why not? Why not? I mean, but
Oh,
do you have any application where have you seen any copper? I mean, I know. देखिए, for publishing, I also want to do copper. But as you ask, and many people are asking copper, I want to understand one thing. Do you see any application? Have you ever
no,
seen a large
no,
copper part?
no, sir.
Oh, then why do we want to do? है ना समझ रहे ना आप बात. If it is a very large, I mean, I never seen copper, but I also
I
want
have
to do.
I have seen with some heat exchangers. In
Heat
some studies, I have
exchanger.
seen it.
What size? What is the size of those heat exchangers?
Not much, sir. It's a medium range only.
So why not? Then you, and very complicated shapes also. Correct. So powder bed fusion is the best for that, na.
Yes, sir. Yes.
Uh, so warm is for large parts, of course, and I want to do, but I think I just want to publish. Uh, I don't think any real application of that. We're not very excited using copper for arc. If you see any application, please let me know. Huh?
Sure,
I'll
sir.
also be very keen.
Thank you, sir.
Okay, thank you. What post processing technique required? ये तो मैंने बता दिया. That's covered, right? All covered.
Yes, Professor.
Fine, fine, fine. So I'll take some more time, Hannah. So quickly I'll show you then. Oh, mm. So other issues, like I said, solidification crack or grain boundary crack, delamination between layer due to lack of fusion. So different material has different issues. Like for example, you see this nice research paper. I got it. I mean, you can check this 2018 research paper. Like aluminium, if I'm depositing aluminium में porosity issues is the major issue. It will definitely come. Some porosity you will see. 5 topmost. But if you talk about, delamination, nahin, nothing. It's low melting point material. It nicely melts, nicely got fused. Stress ka bhi no issues, much issues. है ना? Even you see titanium, to stress no issues at all. But if you see, materials like this binitel and maybe this steels, they have pretty good stress issues. Oxidation, titanium, you know that. You see, it's on top. Titanium is very reactive. You have to do either in a controlled chamber or controlled environment. So this is a nice diagram. You can even somebody can make it now. It's already 6 year old. So many materials have been studied, and this could be a good, uh, you know, useful thing for people like us. This was my first machine in IIT Bombay. I retrofitted 3-axis CNC machine with welding guns. Of course, it was not by me only. Somebody was also working previously, and then two welding guns also mounted together. We can deposit multi materials, one by this, one by this. We made a die out of that. That's how it works. The hybrid process. I mean, deposition and machining together. Depositing, and after that, machining, as per the requirement. Na? Cool. Or of course, now after, 2018, I did that in 2015. Oh, sorry, 2013. They came. Graphitech came. They are the commercialized uh, machine supplier, machine builders, basically based on Germany. Uh, but of course, I made a similar machine in 2013, like I mentioned. This was a video. You can see that aluminium impeller getting built in 2013. Now more than 10 years. So it depositing hub and then depositing blades, and then we'll machine it later on. You see, final near net shape. Now it will get machined to forget the final shape. Correct. Then nowadays I am more focused on robots, uh, and I of course get motivated for using robotic MIG welding in Cranfield. They are the first, basically. They have a company, of course. They have WAM 3D. WAM was the name. Wire Arc Additive Manufacturing was the name given by this group, Professor William Stewart, and this guy standing in behind is Filomeno, who is CEO of that company, WAM 3D. They were the first almost in the world of making the part of commercial level. I mean, the real good big parts. Even titanium. You see the build chamber. They purge the organ inside the whole tank, kind of a thing, and then build. They monitor. You see how nice cameras they have. It's very expensive, but good. But they can monitor each and everything: wire, melt pool, temperature, gradient. They don't allow, because that's how you control microstructure, na? Or you can use parallel kinematics, like this is Stuart platform, inverted Stuart platform, kind of a thing. Correct. I also tried. This was my PhD work. Of course, this is a scissor lift and a serial kinematics on top, parallel on bottom, hybrid kinematics. So that's it. I think I'll just quickly mention about my lab. So we have almost, or let me open another presentation for that. uh, I think for that this should be sufficient, I guess. So I have powder bed fusion. I have 5-axis CNC machine, 3-axis CNC machine. I have 6-axis robotic arm. Now not four, we have seven. I have welding machine, MIG welding. I have around four. 3-axis CNC machine, of course. 1 kilowatt laser I have. It's by IPG and SLA. Not two or three. Now I have more than 20 SLA 20 FDM. I do training uh, programs, a lot of them, and I particularly give individuals one 3D printer so that they can learn from zero. Indigenously, I develop CNC based WAM system, robotic WAM systems, and their CAD CAM systems. So these are my some of the partners on the right. Some of the machines and the parts I made so far. This is Actray. This is bracket for ISRO. There are blades here. Anna, Sachin ji, I'll call you. I'll call you later. And then this is in the my first machine, actually second machine in IIT Guwahati, a robotic system. This was my first machine in IIT Guwahati. When I joined, I just retrofitted, a machine was lying there, and I bought a 2 lakh rupees ka machine, and then I retrofitted it with the uh, CNC machine and converted. And this was a machine I retrofitted in, helped retrofitted in USA, WSU, Washington State University, Pullman, for Amit Bandyopadhyay. Like I said, I do work on software side, slicing and all that. We have our own software, of course, written on top of some CAD CAM packages, and we generate our own tool paths for that. This was my machine, my PhD. It it's its patent number. So this is the multi-axis, what is it? Multi-station, multi-axis hybrid layered manufacturing, MSMA. It has multiple station on top, MIG welding, TIG welding, laser deposition, as well as stress relieving stations, preheating stations, hammering stations, everything on top. And it's an IT with this whole system, the entire machine. Just a minute. Yes. And then, of course, I got a project. This is from IGSTC, like I said. Uh, uh, Here I have plasma. This is the plasma, and in the plasma we can feed multiple wires. Hence, I can make FGMs, functionally graded materials. I do work research in toolpath a lot. That's my bread and butter. What is toolpath in 3D? 3D printing, I believe, like I said, I told you, I'm not a materialist. I don't work. I just do the metallurgy to survive. I mean to publish, to evidence, to get the evidences of some of the claims. But I'm not a hardcore metallurgist. No, we do research in such thing. Those you will find only in the field of 3D printing. We do nothing but 3D printing. Toolpath. What is toolpath? It's like I give you a field, a khet, and I say that you got a tractor, move the tractor, and the way you move is nothing but area filling, and the way you are moving is nothing but the tool path, the path you are following, and the path tool path should follow, the tool should follow. So this paper is published in JMPT. For more research you can do. What we do, instead of moving continuously, we move like this, the deposition head, not straight lines. We call it trachoidal. And trochoidal, when it does, it gives us very interesting results. This is one of the largest metal 3D printed part in the country, 50 kg. It's in my lab. And then surface finish was absolutely good because melt pool stabilizes itself nicely when you move like this. Strength, you see the strength, x direction, y direction, even z direction, very very similar, not much difference, very homogeneous structures. Even you see this large microstructure here, it's very difficult to even find hedge in it. Even we reported some interesting degenerative paralytic structures. It's a toolpath, just like making jalebi. Of course, we didn't get inspired by jalebi. We later on connecting it with jalebi or drop on demand. This is coming. This has not been published, so but it will come soon. Second review came. Here we are depositing one drop only, and then moving to the next place, depositing another drop. Hence, we are depositing drop by drop, and as a result, you can control now cooling rate as well, or you can deposit like this. I mean, of course. So this is called drop on demand. Or I have developed some toolpath. This was published in additive manufacturing. Here you see why to deposit just like this back and forth. Instead, I can deposit any random manner and it's a single line. So the task was this. I give you a pencil and say that you got a shape. Without lifting your pen, you have to build that shape like this. Remember this game? Correct. Now, without lifting the pen, you have to fill the entire area. So not only that we can deposit in this manner, multiple manner. I mean, each layer I can deposit with maybe thousands of different way. Like this, multiple turns. It breaks the thermal gradient, reduce the stresses. No turn, I mean less turns, quite linear, quite circular, correct? Quite radial. They give different properties. But I have this software now ready. Now you can run AI and find out which layer should deposit with which toolpath. Gives you different property. If you have multiple, robot, that also can be planned. This green path is for one robot. This is for another robot. Correct. Also, we can make functionally graded materials. Now, this is interesting. What is functionally graded material? Like you see this sky, right? In the evening, the blue sky and the orange one, nicely getting changed from one color to another color. It's called functionally graded materials. I can control structure. Somebody asked me, can I control? Yes, we can control. I have different microstructures here. I have different microstructures here, and I have different microstructures in here. And in the same sample, I did not do any post processing. Control it while depositing. Not only that, we can have different density. This paper is published in CAD. I can control my porosity with the same tool path, and this tool path is again single line. So we print a bone, we did the reverse CT scan of it. After printing, it exactly matches with the original CT scan. So no need to give porosities, those are engineered. I mean, we just did the exact porosities. I can even print parts, you see the exact same parts, same size, same shape. One is 590 gram, another is 475 gram. You can think about it, how we reduce, I mean, how can we reduce weight out of it while they have exactly same shape. Here are some functionally graded materials. Again, bottom is material one, another material on top. We even see cracks sometimes, yes, when there are issues. We are working on depositing and finalizing how to transit. Should I suddenly transit like here, or should I slowly transit? So that study is going on. Z direction FGM. Or not only that, we can even deposit on a plane. This is a rectangle, and in that rectangle I'll define that I need 0% here, 100% mild steel, and then in this zone I need 100% P91, 0% mild steel. In between, you tell me how to vary, I'll vary. So we sketched this first idea of our plasma system. This is not in the India, but in the world, nowhere you will see such a system. We did a lot of trials, and then we finalized. I mean, of course, we made a lot of small machines, where this kind of 3D printing machines you will see soon from our lab, particularly for FDM. We are making it of now very cheap. They are not expensive, very fast, faster than your FDM, much, much, much faster than your existing machines. And then this is the facility of plasma. We have like multiple facility, even we have lasers, blue laser as well, but this is particularly for plasma. So plasma, both the sides, each wire, each plasma, you can feed two wires. You can see this video. This is the plasma, and there are two wires going into it. You see left wire, right wire. This is P91, this is mild steel. I mean, and they're getting deposited. And depositing the bead. I can feed wire with any feed rate at any location, whatever required. We just don't work in labs. We build machines or help our industrial partners to build machines. Uh, this is one of the success story. This machine was launched in Imtex 2 years before. Very good friend Vishwas from AMS has launched this machine, and they are my industrial partners. Of course, we have softwares our own now with the help of module works as well, uh, which can plan the entire machine. We can put inside a virtual environment and plan its path and everything. Some case studies you can see. Maybe I'll show you the best one, recent one, not best, all are good. Whenever somebody comes to our lab, we don't have anything to show. You know why? Because we don't keep parts for us. We make part and then they are gone. It is currently in New Zealand, I believe. So this is the part we built for a New Zealand company, and it's by aluminium. We built it and we saved around 60% material in it. We deposit and then machine and then give it to them. It's a quite large part. These parts will go underwater soon by January. We are building some parts for NIO Goa with multiple material, somewhere different material. This is the part for forging die of stellite and stainless steel. We are working on it. We work on improving productivity as well. I think I should skip those slides quickly. How we increase, but we are trying to build our nation like this with our tool paths. You see that how we are filling India's map with different strategies. So that's what we do. Thank you. That was warm for you. We do many other metal processes, but I think I do not have time to discuss that. Instead, I will take some questions. This is a good
Okay.
video, but I'll skip it. Let's see it. Maybe on LinkedIn you can see that the dancing robots. Okay, thank you.
Thank you, Professor. Yeah, we have some question. Uh, Apart from Simufact and ANSYS additive, is there any other notable software available to simulate?
Abacus, I use Abacus in my lab, but again, I don't do, sir. We don't do simulation until we got stuck. Currently, let me tell you, until I see a problem statement, we don't really appreciate. I mean, of course, you should do. People should do. There should be researchers on that side. But what we believe, what we are facing right now, the issue. Currently, all of the machines in market, they print the part, then they have to wait till the desirable temperature is reached and then they deposit. But I want to do that management in a way. Here itself I can tell कि भाई you don't make one part, instead make 5 parts, so that deposit one layer of this, second of this, third of this, third. By the time it's ready, come back and deposit. If part is so large, you can't afford. You can even print continuously. Continuously it can print, it won't collapse. So I am doing a lot of that right now. And
For warm process, Professor?
for warm, so I use Abacus.
Okay, Professor.
But it takes a lot of time, and then I use in between cooling, forced cooling also. That how, because after a temperature it doesn't matter, right? You just cool it. Yeah, the recrystallization temperature when it is achieved or below that, you just forcefully cool it na. Why to wait and slow cooling? So for that also we do some research, and then I use Abacus.
So somebody asked about the mathematical model for controlling the kinematics of the machine and tool effect
Yeah,
deposition.
that's the fun part. So we do some maths. You want to read it, read this paper. It's in Journal of CAD. Journal of CAD. Write my name there, Sajan Kapil. You will get only one paper, I think. And there you can see the how do we came up with the algorithms for depositing kinematics. Kinematic. reverse kinematics I use inverse kinematics we use in writing those making those virtual environments, of course. So that's established books, nothing I mean all are simple robots na, serial kinematic.
Yes, Professor.
Now the challenge will come with that machine which I have shown you na, which has
Yes, Professor.
and now I'll, but then again ho jayega, some students should do.
You have shown one machine which is supposed to send Switzerland, right?
New
Yeah,
Zealand, not
New
machine, the
Zealand.
part
Sorry.
already
Yeah,
sent.
that
So
part. Yes, Professor.
that's gone.
Without in every warm process, we will have that staircase effect, right? We have to machine and then remove. Without
I mean, depends. I mean, for example, I build a part. For example, my chair, correct? The bottom
okay,
part of this chair, the cylinder. Why do you need machine for that?
okay,
For example, hook, which is lifting the crane hook. Why do you need machining for that? So
okay,
the robotic arm. Why do you need machining for robotic arm? Apart from only the portion where the bearing will go. So yeah, I mean, we have to be clever on that. I mean, it's not required. Machining is not always required, sir. Even for them, I
okay,
told them. I mean, it's a casing. It required machining inside. They will put some electronics. But I said, why you want machining? Put it, na. I mean, even if it is this bottle is not machined, it's of metal. It's okay, right? So it depends.
okay, Professor. And we have a question from Ravi Bhatt. He asked about he used helical toolpath, but not achieved the appreciable results. So he
View
asked
from
about
वाह बढ़िया नहीं helical नहीं है तो crocodile बोलो. Don't call it helical. Helical goes up. You are in a plane, and then you are moving. Then it's called crocodile. Very interesting result. Don't give up, please. My student, PhD, 6 years just on that. First year, very irritating results. You have to just modify 2 3 things. Read that paper. That paper is in JMP, JMPT, Journal of Manufacturing. What is it? Journal of
process and technology. Process and technology.
JMPT. There is a paper called Trochoidal, and Trochoidal paper you read by us. Maybe you can search that, and you will find that results. You will see the issues also. And one of the what is the issue you are facing? If you can type that also, I can help.
Yeah, Ravi, but can you type your
Or maybe unmute Ravi. You can talk, Ravi.
Professor Ravi? Are you there? Okay.
Am I audible?
Yes,
Yes, yes, yes, Ravi.
Hello, sir. Actually, we have suffered with the melting and demelting of the helical type of toolpath we have selected. In that case, we have successfully completed the cylindrical one, but we couldn't achieve the appreciable results in the helical one, or spherical, we can say.
Should not be the issue. I didn't understand. Helical means cylindrical, helical. What is the difference?
Sir, actually, the tool is moving in same axis circle, then drop down, then again one circle, then drop down. But in the helical part, it will continuously moving in the XYZ plane.
ठीक. Yes, you are right. तो ऐसा है. I know what has happened when you are depositing helically, correct?
Yes, sir.
Then your part got fall, right? I mean, it got heat too much, na? I know, है ना?
Yes, sir.
So you should that's what I said. You have to do simulation and see that what size of part you should build. If it is a very large part, then you helical will work, because
Mhm.
by the time torch come back, the temperature should be reduced, na, enough that
Yes,
it
sir.
can sustain.
It will be
Correct?
solidifying.
So what you do, if you really want to do and don't, you are not worried about microstructure, cool it forcefully. ठीक है
Okay,
ना?
sir.
There's one robot going ahead, and then उसके पीछे से you put another pipe in which air is coming, let it cool. I know microstructure issues will be there. We'll resolve it later. है ना?
Okay, sir. Thank you. I will be touching with you
हम्म,
for some future complications if we have faced.
बात करेंगे ना. Good.
Thank you, sir.
Okay.
Aravind asked one question, Professor. Do we currently have any efforts to do a multi-length and timescale finite-based simulation model for
Multi-scale
DED process? He asked.
I want to read
Yeah,
it.
6.49, 18.49 time.
18.49, 18.49। आप सुनो, अब मेरे को 15 मिनट लगेंगे, हाँ मैक्स। हाँ अब 18.49, 18। हाँ हाँ, थैंक यू। डू वी currently have any efforts to do a multi-length multi-length and time scale variation from micron to build volume size for DD project? Do companies invest on commercializing such models? Yes, I think I cannot answer that multi-length. What does it mean and time scale? Because I'm not from a finite element background. So, but I think what you want to say is, can I simulate a small part? I believe, which gives me good enough results applicable for the large part. Correct? If that is the case, yes, ANSYS has that. Even in powder bed fusion, they do not really move the heat source. They switch on the entire layer suddenly, and that's very fast. The simulation, of course, it doesn't give you very close result, but approximate bata dega.
Sir,
So
which orientation is best in powder bed additive manufacturing? Which will provide good strength, sir? Which orientation?
the in which the laser is moving, they say that that's the best, the direction of
Oh,
laser.
like 45 degrees, we can.
Oh no, you cannot. Okay, you are saying that. I mean, I don't know. Then yeah, of course, 45 will be a mix of both. So that's, but best you said, na? The best will be along the laser. So that means 0 degree.
Okay, thank you, sir.
So, sir, we
So,
have a
am I audible,
conventional
sir?
part. Yes, you can
Right.
ask.
So this is Arvind, and to just clarify on the multi-length and the multi, let's say, length scale across different length. What I meant is there a model which inhibits or which takes care of uh, let's say modeling something from the scale of microns to build volume size. Let's say, for example, I give an input of a fixed current density and the layer thickness, for example, in powder bed fusion process. Would the model give me, let's say, the grain size, which is in microns, and say the residual stresses, which might not be in microns, and say the tensile strength of a part, which is in let's say in build volume size. So what I'm saying is there one such a so-called God model which incorporates everything, which basically simulates the entire process in itself? So that is my first question, and the second question is a simpler one, which I believe you have already answered that. Thank you.
Thank you. I have no answer for that. I'm not sure. I use only Abacus, sir, and that too when required. So I do not even explore much of these. Other software I use is EDAM because I'm interested in discrete element method. I do work on that. Otherwise, we do only CAD CAM. I don't think I should not answer that there is no software. I am not aware of any such software which can give you all those properties. But I think there are more qualified people than me who can answer it. I am not very much qualified for that, I think.
Thank you, sir. Thank you, sir. That is actually much helpful. And if you could just reiterate the first point that you said, which to me sounded very clever, which means do simulation only when it is needed. So I guess like you said something on those lines. So personally, on a level, I feel like that point is quite good because, like from my experience, one simulation takes 6 hours
Yeah,
in the minimum, right? So to me, like at one point of time, I pretty much get annoyed and I just cancel the simulation and say try to interpolate the errors in my head. So yeah.
you are right. We're right. We bought a entire one of my consultancy project. I didn't get took the money. I said to give me a big computer. Many of my students are facing this issue. But again, we don't do it for fun. No, I mean not for fun. I should say we don't do it for research. Just we don't imagine and develop a model. No, we try to get answer for my question. Like somebody asked, but asked just now that helical he is not able to build. Exactly, we are not able to because we cannot predict. We even predict that. My simple question: 10-meter diameter, correct? Can I print continuously? No, it has to be a different diameter. But what is that diameter? My simple question, I cannot readily find it in a paper. We are trying to find those answers. That what diameter, what perimeter? Let's say if somebody can tell me, sir, okay, 30 perimeter is okay with 130 current. Enough information, very good information required for all industries and everybody. Ki, theek hai bhai, 130 parameter perimeter. If it is there with 120 current, it can be printed continuously. Means helically. You just keep on printing and just go home. है ना? So yeah, thank
Professor,
you.
one question. Actually, we have a warm process. We have very BBF process. I am printing a same material. Can you tell me the properties like strength and microstructural and application wise? Can you? Uh,
Yeah, I mean, of course, first of all, you will have a better micro. What is better? I don't know. I mean, in that, I always have this doubt. But there is no better, right? Microstructure. Somewhere you
yeah,
need
maybe
martin
smaller
side.
micros. Yeah. Okay.
So
Okay. Grain size. Yes, Professor.
Maybe
you want
equiaxis, sir.
you said homogeneous, right?
Yes.
Homogeneous
Yes.
property. I still find more homogeneous property in warm because their
Okay, sir.
dilution is high. I mean, it's quite, it penetrates enough, a lot actually. Then powder bed fusion. I feel that I saw whatever paper. The homogeneity is better in warm because it penetrates more. But again, on a cost of bad roughness, very very bad roughness.
Press distance. Yes. Okay, Professor.
Which one is
So,
finer and coarser, sir?
Finer. That I again, it depends on the cooling rate, right? So cooling rate is quite slow and controlled in powder bed fusion, as in compare of warm because it's in open environment
open.
and have not much control on that. So that should be fine. Yeah, the powder bed fusion.
Okay. So, is there any question from the participants?
All are covered. Is there
The
additive?
Yes,
one
Professor.
final question, sir. Uh, so
Is there a? Sorry, sir. I was reading some questions.
that is what I'm going to ask, sir, for our students. That is
Is
the
there
question, yes, sir.
additive manufacturing based student chapter on additive manufacturing? Could you suggest some of the Sir, I do. That's my second job. So you can explore our amlab.in. This website is with error, lot of errors right now, but luckily I got this domain amlab.in. It is my website, our group's website. Here, if you go to HRD section, I'll show you what is good for students here. Just give me 1 second. My PC is blinking. I don't know why. Yeah, amlab.in. And here HRD. In HRD activities, if you see online courses, I have this fundamentals of additive manufacturing technology. Have you seen this course, sir?
Professor, we are undergoing so many. We are
I have
doing two
taken it
diploma
twice,
course.
sir.
Yes, Professor. Twice.
So this is I think I don't think I have put more effort than this anywhere on
Yes,
theoretical
Professor.
background. Online, though, I don't think I even don't teach 3D printing in IIT Guwahati, and I don't teach it because I don't think then I can justify teaching so many times same things. So this was one of my best effort on theoretical side, but how to make it more practical side. So for practical side, I do courses. Let me show you that. I think, yeah, this is full of resources. Now look at this website. This is, for example, somebody wants to learn CAD CAM, SolidWorks.
Okay.
So there are 4 lectures on YouTube. You will not find it without clicking here because they are hidden. Uh,
Okay.
but they are very detailed ones, quite old now. I built it in COVID. They can learn SolidWorks in like just 4 lectures. And somebody wants to learn what is math really. uh, I teach maths, so that is here. You can get all my slides available. So maths, all that learning resources are available here. You can explore this. So math I teach, for example, I don't know if you can answer anyone here. How do we multiply two metrics? Somebody, how do we multiply two metrics? You have matrix A, matrix B, na? How do you multiply?
Yes, Professor.
How do you multiply? Maybe. So we take the row first.
Row, yes,
matrix.
Professor.
Row and
And
column
then
wise, sir.
column, yes.
Why? ठीक है. So there are many things. So that's why I picked maths later. I mean, I don't know
Okay.
why. So that
This,
itself will take a lot of time. There are good YouTubers. They are answering it better than any book. So best resource nowadays, sir, you asked to answer your question quickly, is YouTube. And there is a MIT graduate called 3B1B. He has a channel. You will learn math much better than anywhere else. Even I learned it from there. So YouTube is this resource. I hope I could answer it, sir. Or yes,
okay.
like I said, I have bought 2020. I have right now 15 FDM, 15 SLA. Whoever come, I give training. The student are supposed to not only listen, they have to make part. They got individual printers, and I'm going to make those 50-50, 100 by 2025 December. So I'll be having 100 printers on which the student just print PLA.
Okay. So if there are no question, you can propose a vote of thanks. Professor, you have to wait for 2 minutes at least for the vote of thanks because we have to introduce you. Ranjit sir, are you there?
Am I audible, Dr.
Yes, Professor, you can.
Okay, time to give the vote of thanks. Good evening, everyone. It is my privilege to propose a vote of thanks on behalf of St. Joseph's Institute of Technology, Department of Mechanical Engineering. First and foremost, we would like to extend a heartfelt gratitude to Dr.Sajan Kapil, Assistant Professor from IIT Guwahati, whose invaluable insight and expertise have made today's session a resounding success. Your session has undoubtedly enriched us with new perspectives, and we are confident that the knowledge shared will significantly enhance research capability of our teaching community. We would also like to extend our gratitude to the previous guest speakers, namely Dr. Jinoop, Dr. C.P. Paul, Dr. Pratik Saxena, and Dr. K. Sendil Kumaran for their valuable thoughts. A special thanks to our organizing committee, Dr. N. Tangapandian and Dr. M. Crispin Das, who worked tirelessly to ensure the smooth execution of this program. Your dedication and attention to the detail have truly paid off, and we deeply appreciate your efforts. A special thanks to our beloved principal, Dr. S. Arivalagan, and our respected HOD, Dr. D. Elil Raja, whose constant support has helped us to conduct such programs. We would also like to thank all the faculty members from various institutions who took the time to attend and engage so actively throughout the 5-day session. Your enthusiasm and commitment to continuously learning are truly commendable. Last but not certainly the least, we would like to acknowledge the support of our administration, who constantly encouragement and assistance make such an initiative possible. As we conclude the enriching program, I hope that we all leave here with new ideas, strategies, and a renewed commitment to excellence in research. Let us apply the knowledge gained to foster an environment of growth, innovation, and academic success. Thank you once again to everyone involved. We look forward to more such fruitful learning experience in the future. Thank you.
Thank you. Thank you, Professor. Thank you, participants.
Yeah, thank you. Bye.
Thank you, sir.